Buenas tardes, gracias por acercarse al Salón Meridiano y gracias también a los que están conectados a través del Webex. Hoy vamos a continuar con el ciclo de seminarios que organiza nuestra facultad y en esta oportunidad nos visita el físico Matthew Koren. Matthew posee un título en física por la Universidad Federal de Río Grande y actualmente es estudiante de maestría en física con énfasis en astrofísica en la misma universidad. Ha participado en programas de intercambio académico a través de la Asociación de Universidades Grupo Montevideo, en la Universidad Nacional de San Luis y actualmente se encuentra en la Universidad Nacional de La Plata. Es miembro de la Sociedad Astronómica Brasilera y del Grupo de Astrofísica Teórica Computacional y además colabora en el proyecto SPLAX for NAS. Su investigación se centra en la morfología de galaxias, con énfasis en medios extragalácticos y morfometría multibanda, utilizando técnicas de reducción de dimensionalidad y análisis avanzado de datos astronómicos. Tiene experiencia en observación astronómica, astrofotografía y divulgación científica a través del Observatorio Astronómico IMEF-FUR. Y bueno, el título de su charla de hoy es Morfología de galaxias en el espacio de parámetros morfométricos. Bienvenido, Matthew, y suerte.
Bueno. Thank you for the presentation. My name is Mateus. I'm very happy to be here. It's my last talk here in Argentina and during my exchange here in La Plata. I would like to thank the Dr. Analia for the invitation, for working the Fornax project with S+. And today I will talk about galaxy morphology and how characterize these systems and the classifying of this object in the parameter space with morphometry. The talk here is on the part of my master's in astrophysics in Brazil, and I would like to thank the financiation and support for the research, my university, FURG, my institute, Instituto de Matemática e Física, and CAPES for the support. So, for begin, galaxy morphology is for Greek, shape and study. The study of the morphology is basically the study of the form and rely on the fossil record that reveal the physical process of the universe. Who Bain-Berfield point the direct observational window and fossil record of cosmic evolution. We are now in the era of the data, and we have a lot of images for studying these objects. And the question here, how classify this object? Because the galaxy morphology, it's not just about classification. It's understand the system, or your involvement, and how this involvement, the fusion of or merge these galaxies is approximate for the evolution of the system. And the idea here is how understand the objects present in a lot of images in deep field, for example, of James Webb telescope. This is the idea and why study galaxy morphology. For understand the object and the classification is help us to identify distinct environment and types of galaxies. So a brief history about classification begin this in the epoch of Messier, classifying the nebulas on the skies, and expanding the idea by Dreyer, creating the new general catalog, cataloging these objects for the studies, and this is last year some classification systems of the objects and nomenclatures. The more knowing of the name is Hubble classification, because the Hubble classification is a more simple for understanding, basically separated the wrong name in the early type and late type. Today we know this is a wrong idea, because the early type is not necessarily the early type stage of the galaxy evolution. And another authors help this understanding, for example, genes, and for much of it is knowing the Hubble gene sequence and not only Hubble sequence. And Sanders and Devoclaire extended this idea in the three-dimensional classification, including ring galaxies, bare galaxies, and that's it. The study of galaxy morphology is in current evolution. And the understanding of Cormain and Baillard and Capellari with the Atlas 3D team help us understand the galaxy, and specifically the spherical galaxies. It's not a only branch on this galaxy morphology. That is, the early type galaxies or spherical galaxies have more detailed and have more, the population is more greater than only one branch explained. And here's the question. What do all these classifications have in common? Because what is the question for answer? We need to classify the galaxies with slow rotators, fast rotators. We need galaxies for disks and boxes. That is, what is your question? Why is the chaos of your galaxy classification? But all of these systems have some in common, and a single branch for sphericals. And the understanding of this is relying on the question. It's necessary in visual classification. That's it. We see the galaxies, spherical galaxies, in a ball, basically. But in the spectroscopy and morphometry, we have another characteristic of the system. For example, Graham, 2019, explained more detailed this grid classification, including weak bar and strong bar in early type galaxies, and reintroducing the irregular galaxies, making by Liller's classification 66. But in the epoch, we not see very well the inner structure in this galaxy. But now with the morphometry, we can see another systems, and this is the cause of because Graham extended this grid of classification. That is, the problem is more complex. For this another reason, we need morphology has to go to quantitative. We call this morphometry. The most important single parent today for understanding the spherical galaxy is the CERCIC index, one parametric parameter dependent in the only of this equation for explaining the light surface brightness for radio, explained by Graham. The increases of the CERCIC, it's called certification or galaxy specification. That is one more. If a galaxy is on spherical galaxies or elliptical galaxy, the CERCIC index is increased. Other form for understanding the morphometry, it's only based in the pixel space. We call this non-parametric metrics. For example, Abraham and Conselisi lots explain the idea of the concentration of light, asymmetry, smoothness, and Ferrari 2015 introduced the two new parameters, spirality and entropy, and see the concentration index having strong correlation with the CERCIC index. It's basically they measure the same thing. The CERCIC index and concentration by non-parametric parameters is measure the same thing, the light concentration, basically. So the main goal of our project is understand and moving beyond static visual classification, this boxes classification, it's a spiral galaxies, SEB galaxies, and what, and replacing by opaque black box. It's a neural network is understanding, but we need training this neural network with an interpretable parameter. That's it. How the neural network has the classification of these galaxies without human bias or t-type describing this form of the galaxies. And work in the pixel space, Ferreira 2025, training a neural network based in Lucius G, and apply this neural network on unions, airband, and demonstrate that the pixel space of these galaxies describing one manifold, continuous manifold of these galaxies, but it's only in pixel space. We don't have here the morphometry of this galaxy, only pixel space. The idea is continue this study. The first study is published in the Sociedade Astronômica Brasileira, and we studied the PCA in the domains of the images until the morphometry of this galaxy. The data for this study, we select the EFIGI catalog, 4,400 SDS human classified, plus the same morphological parameters classified by iris on the theme of the EFIGI. That is, this morphological parameter is apparent and involvement, bulge prominence, spiral arms properties, textural aspects, and dynamical filters. That's it. We have a strong and robust classification made by iris of the scientists. And the idea is use this classification, these parameters, for understand or only morphometric parameters, or understand the correlation between. And plus, we have the CVR-HS classification made by Buta. Basically, it's the comprehensive Devanclair-Ivezić Hubble standard extended by Buta, explaining the idea of the stage of galaxies relying the EFIGI Hubble type, EHT, that -6 for CE galaxies and DE galaxies with T-type 11. And EC0, maybe in the 0, -1, and 1 T-type. And we have the family of bars of these galaxies, inner varieties and other varieties. That is the ring galaxies and Lindebrand resonant of the ring galaxies. We have a lot of different classes classified by eyes of this survey. And for study this morphometry parameters, we utilize the morphometric algorithm. Is a fully automatic algorithm for measure this parametric and non-parametric parameter or index, and robust at low signal to noise and low spatial resolution. This is important because this image don't have it's not the James Webb images with high signal to noise. We have now working with galaxies and the stamp images with lower signal to noise. It's important use one algorithm, have the capability for study these objects, these stamped galaxies. And we have use the version 9.66, and for more understanding about the algorithm, I invite you to scan this QR code here. So basically, I don't speak about every parameters, but the principal parameters structured by the Morfometryka is the classical CASGM, concentration, asymmetry, whatever, and the asymmetry improved by the Morfometryka is the rely on classical asymmetry. We rotate the galaxy image and subtract from the original, and the Morfometryka improves for the Pearson-Spearman correlation, and to demonstrate it's more robust at low signal to noise than the classical asymmetry, and smoothness or completeness of the pixels. Basically, we smooth, make one Gaussian filter in the image and subtract for the original, and the same thing, the S2 and S3, the Spearman and Pearson correlation. For concentration, we expanded the idea of the C1 and C2 made by Abraham, the classical concentration, and expanded the idea for the concentration hierarchy, the nice idea developed by Ferrari and your team. And basically, we know the galaxies is more complex that R18 or R20 for the total luminosity of these galaxies. So we spun this idea for one hierarchy matrix of this concentration. The spirality, we have here the original galaxy image And here the normalized galaxies that's not rotated, the polar coordinator of these galaxies, and we extract the gradient field and so extract the mean deviation, desvio padrão of these galaxies. It's proved this strong correlation, this spirality, with T-type of these galaxies, and another authors use it, the combining of the spirality with asymmetry, separating the spheroidal, disk, and peculiar galaxies here. The entropy of the image is based on the channel information entropy. When we have the probability of the intensity of these pixels, and we extract the information entropy, and we need normalize this entropy, and the entropy have on max on the normal distribution, linear distributions. We have more, for example, entropy in these images, but these images, the pixels of the images, the stamp of the images, it's lower entropy than it, basically. So one example of the output of the Morfometryka is here. We have the original image, the model and PSF, the residual, the A1 and S1 map, and a lot of parameters extracted by here, and the curvature of surface brightness here, and the color coordinators of the galaxy for measure the spirality. So you open the capsule first type. Let's go and download the scikit-learn, matplotlib, and make some awesome plots. What I make with all of this parameter? Who characterizes the real manifold and this parameter space? This idea, we are now developed the pipeline called Hydra for basically it's make principal component analysis on this parameter space and make one bootstrap resampling for stability and analysis. That's it. And simplify. In the practice, we use the singular values decomposition for more accuracy and computational time. It's better calculated the SVD that PCA in the practice. PCA is the idea, and SVD is the engine behind this idea. And we have some bootstrap resampling for measure the stability of this eigenvector or these eigenvalues of the PCA. And then we utilize the uniform manifold approximation projection for characterizing the nonlinear correlation between these eigenvectors or the scores of the PCA. We take the scores of the PCA and jogamos in the UMAP for characterizing the nonlinear space to understand the manifold. We have some filtering with key f equal to 0. That's it. The images that don't have any problems in your footage on the Morfometryka, and only select the galaxies, face-on galaxies for understand the bush and disk dominated of these galaxies. And study the overall peak of signal to noise. Don't have a significant loss of the selection. A non-morphological class was lost during the attrition. That's it. We don't less any morphological class in the selection or sample filtering. In natural degrees of the signal to noise, the SE to DE galaxies. That is, the galaxies more diffuse have signal to noise lower here in this space. So the morphometric trends and the EFIGI Hubble type, we see the CERCIC, Gini, M12 decrease. In the other words, the galaxies become more diffuse when we andamos in the T-type range. The asymmetry and spirality increase, tracking visible spiral structures, and Petrosian ratio increase. That's it. These dominant galaxies are more extended. For evaluating the full parameter space, the original idea is put all of this parameter in the PCA for understand the manifold. but we have the bootstrap analysis reveal height variance and instability of the principal parameters. For example, the parameters in the parametric parameters, for example, the CERSIC index, have a strong instability and asymmetry and another classical parameters. And PCA excluding hierarchical concentration shows continuous and uniform distribution. We don't have two main populations here in the PC1. It's more important PC for the model. And the morphometrical space only split in the two distinct populations when hierarchical concentration are included. And so we can basically, here is the PC1 alone capture 80% of the total variance. The bimodality is so clear for here, also the marginal histogram reveal the two distinct galaxy population in this parameter space with only 5 principal components, displaying the high fidelity and low error. And we see the pure spheroidals colored by the T-type. We have in this plot the bulge disk transition here, structural disks, and diffuse disk here. For this, for making comparison with the morphological parameters of the EFIGI, the 16 parameters, visual parameters, we have the strong correlation and the Petrosian gradient separate basically the bulge, the total, it's T-type, basically, and the arm strength and flocculence galaxies. And basically, the PC1 is the smooth transition from bulge to disk-dominate galaxies. When PC2 gradient captures the structural sub-filters, for example, the bar lengths, rings, visible dust, and multiplicity. When we make the connection between the model of only the hierarchical concentration with another parameter set by Morfometryka, we see the PC1 is basically a strong correlation with concentration, CERSIC index. It's not a surprise because it measures the same thing, and the hierarchical concentration englobes all of this concentration. And the PC2 is basically making the size and complexity, and PC3 structural contrast. In other words, we can see only with the hierarchical concentration PCA model reconstruct another parameters and non-parametric parameters. It's the strong correlation between, it's the Spearman correlation here. So when we have the concentration complexity of the systems, we see the PC1 here with lower spirality. We have more T-type galaxies. Oh, that's it. High PC1, low asymmetry, and low spirality confirm the symmetric filter Let's neutral. And this regime in the center left here, because the lower PC1 and higher asymmetry of the pixel image, and maybe the higher structural spiral-driven morphology. In other words, we can see the extremes of the PCs, the principal components, I mean the Euclidean distance of the extremes. We have the PC1 positive, basically is the spherical galaxies, and the negative extreme of the PC1 is the disks galaxies. PC2 the same. We have the extremes of the PC2 galaxies with more structured arms, and negative PC2 more or less inner structures, and the PC3 is the same. We have the ring galaxies here because it's the distinction of the PC1 of PC2. The PC3 is increase the central light of the image and decrease the medium light on the pixel image and increase the older light, a luz que está fora, assim. We can resume this idea of the PC of driver maps in four espaços. Structural disk here with low high spirality and Petrosian radius. Diffuse disk here in this space bulge disk transition in this region with lower spirality and bulge dominance, and spheroidal with higher Cerseic index and Gini, and lower asymmetry and smoothness. When we apply the UMAP in this parameter space, we have the metrics confirm the PCs are linear independent. We have here the Pearson is an identity matrix that is zero number of here. The PC is correctly, but have some non-linear correlation in the other PCs. That is, the PCA is a linear combination, but it still have some non-linear connection between these components. For this, we apply the UMAP with a lot of parameters, new number of neighbors, and median distance of this parameter, and random seed 21, because the computing is not a specifically random process, because this we did on random seed exacta. So we have here a lot of the parameters non-linear making by the PCA. For select the better parameter, we utilize the two metrics, the truth methods, the preserving local neighbors, and that we compare the original distance of this object in the PCA space and the distance in these scores in the UMAP space. And the better the preserve this distance, the better choice, basically. And the Spearman correlation for preserving global continuous distance. And the winner is the NN same and MD 0.00. This substance prevents artificial fragmenters and preserving the true multi-evolutionary gradients of the galaxies. With connection of the physical and morphological visual classification, we have the compact pole and the bottom left. We have the high Cerseic and lowest M12 with near zero visual structures. That's it, no arms or dust in the visual classification, this space. And the complex pole is top right here. We have the domain of structured spiral galaxies and peaks and visual filters, for example, the arm strength, flocculence, visible dust, and morphometric complexity. For example, high spirality, entropy, and asymmetry. Basically, is the question here. The recovery the main stage sequence, maybe, because the sphere of a lenticular galaxy with E negative minor Q0 with dark colors is here, and the confined and the compact bulge dominate pole, and the spiral and the irregular in this pole with this dominate region of the right. Basically, the color gradient is proved at the fluid manifold and the disconnected bins, not disconnected bins. The next steps of my master's in astrophysics is understanding this space, whole clustering this space based on graph connectivity, and training machine learning for classify these objects. So another work in progress, what I have in in La Plata, is the study of the Fornax project with S+ data under supervision of Dr. Analia and Rodrigo Hack, and to Ferrari and the S+ team. Basically, we can see the evolution of the morphometric parameters in the 12 bands of S+, and the correlation with another parameters, for example, the 4000N, tracing the age of the galaxies, extracted by the extragalactic catalog made by Hack 2026 and Morfometrica. And in conclusions of this talk, automated objective filters can be extracted by Morfometrica and the large surveys and low signal-to-noise image, for example. PCA and UMAP reveal the data driving the structures to hide into the human eyes, or to understand this classification of the galaxy only in the morphometric parameters space. And the galaxy form a fluid manifold, not isolated beams. an automated pipeline naturally recover the classical Hubble gene sequence. The idea is we successfully translate one survey pixel in the two astrophysical insights. Other steps is including see the relation with another parameter for mass of these galaxies, star formation rate, and spectroscopy parameters for see when is the fast and slow rotator in this parameter space. We can find these objects, maybe, I don't know, it's one open question on this next step of the research. And that's it. Thank you for your attention.
Thank you. Right now we stand for questions.
Thanks for the talk. Very interesting. And I think that you gave an idea with your last slide, but we were talking about all the parameters and analysis, CA and UMAP. And I assume that you are working on applying this code to different filters and to see if adding this extra dimension of having different narrow ones, class.
Yes.
And if you can obtain insight about morphology or evolutionary peculiarities of the galaxies in much more grouping in more different, making a more specific grouping of galaxies and having a better idea of separating them between
Yes.
spirals, different event design or not, and thinking about the large scale.
Yes. Yes, it's an interesting question because the study is still in progress. The study of the S plus data, we have some attentions in this space using the S plus images because the images is at extremely low signal to noise for extract some information of the galaxies. And we still have some studies on tests about the principle and the first idea is work in the 12 bands of the S+. But the bands, for example, U band, F378, and these lower bands, we don't have some strong signal of the images. This is because that our sample is limited. For example, we have in the literature 100 mil galaxies. What that I know is part of the Fornex cluster, but still was only 402 have in we can see in the S+. So we have 1000 galáxias for 402. This for I'm sorry, I'm very bad with number in English, but 402 galáxias. Only 242 have some nice segmentation by Morfometryka, because Morfometryka needs only the stamp of galaxy and the PSF of galaxy. But we need that the image have the minimum signal to noise for extract some parameter and fit in the equation for extract this parameter. So because this our sample is decreases for 36 galaxies only in 12 bands because the signal to noise of the images. Because this we currently utilize the air band for more abranged number of the galaxies and 142 galáxias mais ou menos. And this one current challenge for whole proceeding the study of the morphometrical signature in the spectrum, morphometrical signature in the 12 bands, because we don't have a good signal for in the 12 bands utilizing the S+. Another searches utilize the DES service for study the Fornax cluster, because it's more highly signal to noise of the images, but not explain better why they use the DES or S+. And your work focus on this and try to describe the morphometrical spectrum in the major part of the bands possible, but we have the challenge of the signal to noise of the image.
Well, but maybe it's a good opportunity to prepare the code and the analysis for different chain paths. Maybe for you because of depth of the images and filters.
Yes. Thank you.